Welcome to the section on the GAN loss. We shall understand how this loss was derived from the GAN paper. Now, the adversarial modeling framework is most straightforward to apply when the models are both multi-layer perceptrons. So basically, that's when we're using neural networks. To learn the generator's distribution PG over data X, that's the real data. We're trying to learn the generator over the real data. We define a prior on input noise. So we've seen this already. We have this input noise, PZ of Z. So here our distribution is Z. That's a fake, and then the real is X. Then we represent a mapping to data space G. That's the neural network, where G is a differentiable function represented by a multi-layer perceptron. So this actually now is a neural network which takes in Z and has parameters theta G. We also define a second multi-layer perceptron D. So D is the discriminator and then G is the generator. D takes in the X and then has parameters theta D that outputs a single scalar. Dx represents the probability that X came from the data rather than PG. We train D to maximize the probability of assigning the correct label to both training examples and samples from G. We simultaneously train G to minimize the log of 1 minus dg of Z. And in other words, D and G play the following two-player minimax game with the value function V G of D. So the minimax of this is now this. Let's now get into the details of the minimax loss function presented in the paper. We have this loss for the discriminator. So firstly, we have to understand that the discriminator and the generator will have two separate losses, or your losses will be seen from two different perspectives. Now, let's start with the discriminator. For the discriminator loss, we are taking the cross entropy loss we've touched already in this course. And with the cross entropy loss, when we have y equals 1, meaning that we are actually having a true label, since y equals 1 right here means the discriminator is saying that the inputted data is a real data. Now, with this output y, which is equals 1, we obviously see here that we have 1 minus 1, which is 0, so this part is taken away, and now we're left with only this, y equals 1, so we have the log of the output of the discriminator. So this is the label, and then this is actually what the discriminator outputs. Now, we can then rewrite this as log of d of x, where d is the discriminator, and x is the inputted real data. Let's look at the log function here. So the log function looks like this. And so when our input data is real, our aim is that the discriminator should output a 1. And once the discriminator outputs a 1, the log of 1 is 0. We could see clearly from here that when this loss is 0, we add this point. And at this point, we have the maximum value, which is L equals 0. That is when the d of x is equals 1, we have this maximum value right here, because these other paths aren't considered, since the value of d of x, because this is actually d of x, the value of d of x. So instead of having a log of x, we could replace this with d of x actually. And we can now have this. And since, as we said, d of x lies between 0 and 1, the maximum or the highest possible value we could get for this function is 0. So once we have this loss equals 0, our d of x equals 1. So the aim here is to maximize this log of d of x. And then when y equals 0, that is, we're supposing that our input is coming from the generator, so it's actually fake data which has been generated. In that case, y equals 0, this is taken off. Y equals 0, we're left with this log of 1 minus y, and then we have the loss, which is equal to the log of 1 minus the discriminator of the generator of z. So actually our x here, our input, is coming from the generator, and obviously the generator is taking inputs from the Z distribution. So we have 1 minus d of g of z. So in this case, we are making use of this other function. So this is what the log of 1 minus d of g of z, where we have this and then this, looks like. So in this case, since the d of g of z lies between 0 and 1, and in order to make sure that the d of g of z is equal to 0, since we're trying to train the discriminator such that whenever it says fake data is able to output 0. So our aim here is to make sure that d of g of z is equal to 0, unlike here where we wanted d of x to be equal to 1. So if d of g of z is equal to 0, then we have log of 1 again. So log of 1 equals 0. And then we could see again from here that when we maximize this, so when we have our maximum value for the log of 1 minus d of g of z, we actually have the loss to be equal to 0. So this again tells us that we should try to maximize this log of 1 minus d of g of z. So in conclusion, we have that our aim here is to maximize the expected value of the log of d of x plus the expected value of the log of 1 minus d g of z. There was a slight error right here. We've modified that. Now we have the expected value of this, where our z is from this distribution p of z. And then if we move to the generator loss, we have when y equals 1, that is for true levels, we actually take this off because you see clearly from here that this loss doesn't depend on g. Now when y equals 0, we have this log of 1 minus dg of z, and our aim for the generator is to produce fake data such that d outputs a 1. So the aim right here is to make sure that whenever we have the generator giving an output, the d of that output is a 1. So in that case, we have 1 minus 1, which is 0. So we'll say that the discriminator and the generator are having two different objectives, although the discriminator actually helps the generator in achieving this objective. So they're actually fighting and helping each other at the same time. So at this level, we have the log of 1 minus 1, and the log of 0 is not existent, but the limit as x goes to 0 of the log of x is negative infinity. So from here we see that as dg of z, which is this, is tending towards 1, we are approaching negative infinity. So in order for the generator to produce very realistic data, it needs to have this dg of z approach 1 as much as possible. And that said, our aim here is to minimize the log of 1 minus dg of z. We shall now compute the loss for the GAN, or for the DC GAN. This is made of the discriminator loss and the generator loss, as we've seen in the papers. For the discriminator loss, what we're having here is two subparts. The first part, we're considering that the output we get is real output, that is output from real data, and then the second part is a fake output, that is output from fake data. And if you notice here, we're having the binary cross entropy of this ones like. Now the 1 is simply because we're supposing that if we are dealing with real output, then the output should be 1. So we're comparing the 1 with the real output. And then for the fake data, we're supposing that if it's actually generated data, then we should have a 0 in the output. So that's why we compare a 0 with a fake output. And then we add this 2 up. With the generator, we just have one part. Now basically here, we're supposing that if we get in data that's been generated, then its output should be a 1, because the generator is trying to fool the model into thinking that its generated data is actually real data. So let's run this now, and then we go to the next part.